Hey guys, we are moving on to exponential decay, and if you notice, I used the same picture as I used for 7-1 exponential growth, but I flipped it because that's essentially what it is. It's going to be the same thing going in the opposite direction. So when we had exponential growth, our coin stacks here were increasing, and now with exponential decay, we're going to be decreasing. Hello. Doesn't want to move. There we go. Oh, too much. Things are going crazy. Okay. Starting with number 1, we're going to graph f of x equals 3 to the x power. So let's make ourselves a t-chart. My computer is going slow and it's making this weird. So we know f of x is the same as y. So if I plug in 0, 3 to the 0 power, anything to the 0 power, is 1. If I plug in 1, 3 to the first power is 3. If I plug in 2, 3 to the second power is 9. And if I plug in 3, 3 to the third power is 27. Okay, so I can plot these. 0, 1, 1, 3, 2, 9, and I'm off my graph. And we remember that this is a, again, I'm sorry, this is going to be weird because my computer is going so slow. Okay, so this is exponential growth here, which is what we worked on in the last section. And remember, I totally missed that point and that one. So let's move that up a little bit. That's what an exponential growth looks like. So what is the change in y value for every x? Well, we're multiplying by 3. Okay, so let's see the second one down here. F of x equals 0.5 to the x. Well, if I plug 0 in, anything to the 0 power is 1. If I plug 1 in, 0.5 to the first power is 0.5. If I plug 2 in, then I have 0.5 squared, which is 0.25. And if I plug 3 in, 0.5 to the third power, calculate that, is 0.125. So when I go to plot these, I have 0, 1 again. I have 1.5, 2.25, and 3.125. Yeesh, that's not really giving me a good picture. Kind of flattening out here. I wonder what happens if I were to go over this way. Well, if x were negative 1, 0.5 to the negative first power is 2. So I'd have negative 1, 2. Let's try another one. Negative 2, 0.5 to the negative second power, I get 4. So I'd have negative 2, 4. Let's try some more. Negative 3, so now I'm doing 0.5 to the negative third power, and I get 8. So negative 3, 8. Well, that gives me a much better picture here. So now I can see that I'm doing this. Not the best, but can you see that it's the same type of curve as my black one, just flipped around? So that's what I'm saying. When exponential growth and decay, they are very similar. They're just flipped. Okay? So how do you tell, looking at an equation, if something's exponential growth or exponential decay? Well, look at the two equations we had here. They both had x's in the exponents. That's what makes them exponential. But then we have to figure out, based on the numbers, if it's growth or decay. And maybe you see it. You still have your normal standard form. We remember that a is the initial amount, your starting amount, and remember that always occurs when x is 0. It would be your y value. And b is your growth factor, or decay factor. So it depends on what the number is, whether it's growth or decay. And here's the rule. If b is greater than 1, it is exponential growth. if b is between 0 and 1, this is just fancy notation for b is between 0 and 1, it means b has to be greater than 0 but less than 1, then it's exponential decay. Notice b is never equal to exactly 1, because if we're exactly 1, an exponent of 1 isn't going to make anything different. For example, if I had 4 times 2 to the first power, whoops, I did that wrong. Rewind. Pretend I didn't say that. If I had 4 times 1 to the x, if b were exactly 1, no matter what my x is, I would still always get a 1 for this. Okay, so that would always just be 4 times 1, which would always be 4. So we can't have it exactly 1, or we don't have an exponential function. Okay, so for numbers greater than 1, it's exponential growth. And for numbers between 0 and 1, it is decay. So we're talking what here? We're talking fractions, decimals. Okay, less than 1. We don't have negatives. B also is not negative. It's not going to be a 0 or exactly 0. It's not going to be negative, and it's not going to be exactly 1. Okay, I have a bunch of examples on your paper. I have a column that says exponential growth, and I have a column that says exponential decay, and I just want you to copy the examples where they go. So we're going to look at them one at a time, equations and graphs. First one, we have an initial amount of 1/2. We have a growth factor of 4. It's definitely exponential. It has an x in the exponent. Is it growth or is it decay? Well, the way you tell is your b, your growth factor, is it greater than 1 or is it between 0 and 1? Greater than 1 for sure is, so that makes it exponential growth. So it's all about that number. Okay, y equals 2 to the x. What do you think? This one, and this one. Okay, so for these 4, I want you to pause the video and try and decide if those are exponential growth or decay, and then we'll go over the answers. Okay, check those out. See if you've got them the same way I do. Here, your growth factor is 2. That's greater than 1, so that's growth. And again, your growth factor is 2. So there's your initial amount. Then there's a -3 back here. You can always add and subtract numbers here. It'll move your graph around. But you're still focused on your a, b to the x part to decide what is going on, growth or decay. Over here, your growth factors are decimals and fractions between 0 and 1, so those are decay. When you're looking at a graph, are you growing? Are you going up from left to right? Or are you decaying, going down from left to right? So what is this one doing? It's growing. So you can draw that example. Let me put a line right here. That would be a growth. How about this one? It's also growing. How about this one? Growing. This one, ooh, that one's going down, so that's decay. And then finally, decay. So make sure you have all these examples written in your growth and decay columns so that you can know the difference based on equations and based on graph. You're welcome. Okay, sketch the graph by filling out the t-chart. Find at least 3 points even if they don't all fit on the graph. Okay, so take a look at these two. They are both decay. Your growth factor is less than 1, but greater than 0. I'm going to pause the video. I want you guys to try a couple of these first. Okay, so hopefully you notice if you just did positive values, you didn't get too much information. You're only going to get these 4 points. But if you start using some negative points going backwards, you end up seeing that exponential curve. So a lot of times on exponential decay, you're going to have to use some negative x values, and that's perfectly fine. If you haven't already done so, pause and do this next one. Maybe try some negative values as well. Okay, -2 was way far off my graph, so I just plotted from -1 down to 2. Now, sometimes students will assume that this is going to happen, but let's try plugging in, I don't know, let's try plugging in 10. So 1.6 times 0.25 to the 10th power. And if you do that, you get a very, very, very small number. It's in scientific notation, but it's positive. So this actually will keep getting closer and closer and closer to 0, but it won't actually go into the negatives there. It's actually an asymptote. You don't need to know that word, but you will learn it more in Algebra 2. So that just flattens out. So you want to make sure these look like exponential graphs. Don't make it a straight line. It's an exponential curve. Okay, given the following table of values, create an equation that fits these points. So the first thing you want to do is figure out what is happening from one to the next. So here it looks like, okay, I'm subtracting 400, subtracting 200. So immediately I would think, okay, maybe I want to do something besides subtraction since that's not the same pattern. Another thing I could think of is that I have divided by 2. Divided by 2. But remember what we've been doing. Even back in Unit 6, we're talking about addition for linear or multiplication for exponential. So I don't want to do divide. How can I make divide by 2 into multiplication? Well, dividing by 2 is the same as multiplying by 1/2. So is that what I'm doing the whole time? Am I multiplying by 1/2? Sure. Multiply by 1/2, multiply by 1/2. Okay, all right, so I know my growth factor. So I go to my generic form, my y equals a b to the x. Y is y. A is your initial amount, which occurs when x is 0. So that would be 800. Times b is my growth factor. That's 1/2 to the x power. If you're not sure if you have the equation right, you can check it. Plug in 5, and you should get 25. So 800 times 1/2 to the 5th power, and sure enough, I got 25. So my equation looks good. Pause the video, you guys try it with this one. If you are having trouble figuring out what you are multiplying by, you can always work backwards and divide. So if you do 30 divided by 100, that gives you 0.3. So what that means is to go from 100 to 30, you must have multiplied by 0.3. So that means 30 times 0.3 should be 9, and it is. So we're multiplying by 0.3 on each one of these. Go ahead and check that. Then your equation, your initial amount is 100 times your growth factor is 0.3 to the x power. Okay, on the last section we talked about percent increase. Now we have percent decrease. It's the same thing that we've been working with your y equals a times b to the x. It's just when you are given a percent and not a growth or decay factor, if you're given a percent, you have to use this part of the formula to find your b. And when you are decaying or decreasing, you're going to do 1 minus your percent. But key factor, and some of you guys were struggling with this in the last section, you have to change it to a decimal. So if you are given 52%, you must take that number and move that decimal 2 spots. So when you go to plug it in here, it has to be 0.52. It'll be 1 minus 0.52. All right, let's try number 11. A new, I left that out, a new car is worth $20,500 and depreciates by 5% each year. So y equals a times b to the x. It's always your formula. A is your initial amount, which here is $20,500. And then because it's depreciating, that's going down. So 1 minus, I can't put 5. I have to take that 5% and change it into a decimal. So this decimal point that's right there has to move 2 spots, which means it's here, and I have to fill in a 0. So 1 minus 0.05 to the x power. Cleaning that up, it's 20,500, and then 1 minus 0.05 is 0.95. Keep in mind that if you have a decay, a decreasing, a depreciating, anything that's going down, this number, what you end up with, has to be between 0 and 1. If it is not, you've done something wrong. So that's a really easy way to check. Because if I would have just done 1 minus 5, if I wouldn't have changed this, I would get a -4. That's not between 0 and 1. So a quick way to check it, make sure that number is between 0 and 1. Pause the video, you guys try these next two. Okay, check your work on these two and see what you have here. See if this works out correctly. See if you have the same answer that I do. Okay, the pesticide DDT was widely used in the United States until it was banned in 1972. The problem with DDT is it's toxic to a wide range of animals and aquatic life and is suspected to cause cancer in us, in humans. In science class, I think you guys have dealt with half-life before. The half-life of DDT can be 15 or more years. In this example, we're going to say it's exactly 15 years. If you don't remember, half-life is the amount of time it takes for half of the amount of a substance to decay. So how long, if I have a certain amount of the pesticide, the half-life is how long it takes for half of it to decay. Scientists and environmentalists worry about such substances because these hazardous materials continue to be dangerous for many years after their disposal because it takes these half-lives to get rid of them. So if there were 100 grams of DDT, how many grams will be left in 45 years? Well, we're talking about half-lives, we're talking about decay. So we need to be talking about exponential decay. The initial amount that we're starting with in this problem is 100 grams. And we're talking about a half-life. A half-life. So what's the decay factor? It's 1/2. And we are asked to find it for 45 years. Okay, but how long is 1/2 life? It's 15 years. So if we are looking for a time period of 45 years and each half-life is 15 years, that's a total of 3 half-lives. So 100 times 1/2 to the third power gives us 12.5. It's a word problem, so we want to label it 12.5 what? 12.5 grams of DDT. So you can see why this would be a problem. After 45 years, you still have 12.5 grams of this stuff left. And they didn't use grams. They used, thousands and millions of tons of this stuff and poured it on crops and things to keep the pesticides away. The problem with it is there's still lots of it left, and it causes cancer, and it's toxic to animals. So that's obviously why they banned it, but you can see the issue with it. Okay? And by the way, if you didn't think about it, 1972 plus 45 years, it's 2017. So you're talking about this much stuff left just last year. Okay, so there'd be just a little bit less than that left this year. And again, you're thinking tons, not grams, millions of tons. Okay, and then lastly, for each equation, identify the initial value and the percent increase. Initial value, right there. And then your percent increase. If this number is between 0 and 1, to find the percent increase, you must do 1 minus the percent. That's what that number represents. Okay? That's what we were told back here. 1 minus the percent. So, to solve this, we could subtract 1 from each side. So our percent would be 0.516 minus 1. That gives us negative 0.484. Well, we'd have to get rid of a negative sign, so our percent is equal to 0.484. But that's the decimal version. To make it the percent, we're going to take it and move it 2 spots. So our percent increase, should say decrease, change that on your paper, is 48.4%. Pause the video, you guys do this last one, and change that to decrease. Okay, your initial value is -8. Keep in mind that this represents 1 minus your percent. So 1 minus your percent is 0.2. If I'm solving this equation to try to find the percent, I need to subtract 1 from both sides. So I get negative percent equals 0.2 minus 1, which is a value of negative 0.8. I would have to divide both sides by the negative, so I get the percent equals 0.8. Keep in mind that's the decimal version, so we need to take that and move it 2 spots over, which gives me a percent decrease of 80%. Okay? All right. I'm just using this percent sign as basically a variable. You could choose to use a letter there, it doesn't matter, but it's just a symbol to represent our unknown. All right, you guys go ahead and finish your packet.